we go. And then I will share again. So as I was mentioning, this is a panel discussion about a geochemical context for prebiotic plausibility. This is an IPLU panel discussion. The IPLU is the Cambridge Initiative for Planetary Science and Life in the Universe, a group of researchers at Cambridge that are interested in the questions of how life might have originated on Earth and how it might originate on other planets, and the related question of, are we alone in the universe? If you are interested in events that touch on these particular topics, I recommend that you go to the web address listed below. So when I first started to think about redox chemistry for surface environments and for prebiotic chemistry, the first thing that I started to think about was giant impacts. And one of the reasons for this is that a lot of prebiotic chemists have gotten very, very interested in giant impacts because they end up producing these reducing conditions. And these reducing conditions are very, very useful for certain key prebiotic compounds, some of the ones listed here: hydrogen cyanide, cyanoacetylene. I'm not sure if it's on here, but it should be formaldehyde. Giant impacts are important because they can make molecular hydrogen, and they do so because they carry metallic iron with them, and the metallic iron will react with the water and produce hydrogen and oxidize the iron. Hydrogen can lead to reducing conditions, and prebiotic chemistry needs those reducing conditions. Also, hydrogen is a source of food, effectively, for early life. This is a picture of Hydrogenderbacter thermophilus, a thermophilic bacterium that consumes hydrogen. And some environments are known to be sources of hydrogen, either through breaking down biological material or through various abiotic processes. There are various pictures here: methane bubbles from the Sudan mine. Methane is known to degas from mud volcanoes, such as those in Azerbaijan. And serpentinization is thought to be responsible for hydrogen degassing in underwater hydrothermal vents. And of course, it doesn't always need to be endogenous. You could have exogenous sources of reducing power, such as the comet pond scenario, where a comet lands softly on the surface of Earth, and the materials of the comet end up providing these sorts of reducing conditions and potential food for early life. So we are going to be talking this time about geochemical sources of H2, so other ways to get H2 besides impacts or besides exogenous sources. And this won't be exhaustive, and it's not even exclusive. These different sources can be present in the same environment. We are going to be hearing about H2 generation and reducing power of iron silicate rocks by Alexis Templeton, fluid mixing and low temperature H2 production on early Mars and maybe Earth by Nick Tosca, and Barbara Sherwood Waller will be talking about radiolysis and H2 production in underground waters. The format for this is each of the speakers gets 15 minutes to speak, followed by 5 minutes for Q&A about that particular talk. Then there'll be 20 minutes for the panelists to interact with each other, 20 minutes for Q&A, and then I will make a brief concluding remark. So again, thank you all for being here, and please join me in thanking the panelists who will now be presenting some of their research and thoughts about this interesting and important question. So we will start with Alexis Templeton.
Just a sec. I can already see there's a problem sharing. That's good.
It looked like it was starting, and then
yeah, right. I saw. It's funny. I learned enough with enough teaching this year. There was you could tell when there was going to be a problem. Okay,
Oh.
it looks all right. Looks all right this time for me.
Yes.
Don't know why,
It
but
looks
that's
good to me.
good. Yeah, so, Paul, thank you. It's wonderful to speak with you. I always enjoy doing it. It's a real treat to be here with Nick and Barb today. And my talk should be about 15 minutes. Because we're a small group, I'm going to just relax a little bit and not worry too much about exactly if I'm hitting that. I promise I won't try and go too long on those slides. And I'll just start to open this conversation about hydrogen generation, particularly looking at it at a rock-focused perspective and interest in iron silicate rocks. And in my career, I've long been interested in hydrogen and different pathways for producing it, particularly through water-rock interactions. And it's often for me been connected to its fate, particularly in biological metabolism and looking at primordial metabolisms or organisms that can grow autotrophically using hydrogen as a key source of reducing equivalents in their metabolism. But over time, then I've also become much more interested in the importance of hydrogen-rich environments, I guess, in terms of their potential role in prebiotic chemistry. And so again, interested to join that conversation today. But for me, I often think of, well, how are we going to get hydrogen? But I just want the hydrogen then to be able to be split and for electron transfer to happen into power processes downstream. But in terms of producing that hydrogen, it comes back often for me into the rock system. What's the word we often use is protolith, or what's the rock material, its chemistry and properties that might give rise to hydrogen generation. And there's such a broad and deep field of both thermodynamic modeling, field observations, and laboratory experiments. And they really needed to keep connecting with each other because our thermodynamic models have been increasing in their sophistication as they start to better incorporate the real mineralogy, especially the minerals that are formed through water-rock interaction and their iron chemistry. And the field observations keep surprising us and are telling us that maybe our experiments and our models aren't right. And they, again, shape that. So some of those things I think are going to come up through our different presentations today. In brief, when you go into any kind of geologic system on the modern or ancient Earth or on other planetary bodies in our solar system, the majority of rock types are mafic and ultramafic rocks that when they get exposed to near surface conditions and are in contact with water, they're inherently unstable. So there's always a thermodynamic driving force for these types of rocks in contact with water. And in particular, the focus is often on specific minerals within those rocks, such as olivines, pyroxenes, and plagioclase and other feldspars to some degree. And I'll specifically talk more about the extreme end member today of these so-called ultramafic rocks. So they have magnesium, iron, calcium, silicate minerals that dominate the bulk chemistry. And then a lot of the interest is particularly in the redox active properties of those rocks. So it's a matter of really understanding the changes in the iron distribution between different minerals and its oxidation state and what controls that at different points in time and depending on the geological or the planetary conditions under which they're getting exposed to water. So broadly, when we talk about ultramafic rock hydration, olivine and pyroxene hydration, in these magnesium iron silicates, we're talking about serpentinization, of which you could go into hundreds and hundreds of papers that explore different contexts in which serpentinization has been observed in these rock types that have undergone hydration, Earth's surface, both in marine and in terrestrial settings. And overall, if you're looking at that literature, you're looking at examples of where magnesium iron silicates have reacted directly with water. And in that, they're forming minerals that are stable at lower temperature conditions or near surface conditions. Serpentine being the dominant mineral, that's why the process gets that name. And a bunch of other mineral types that can form, and some of the most common, but not the only ones that would form, would be things like magnesium and iron hydroxides, oxides. And the great interest is in the molecular hydrogen, which is one of the byproducts of that reaction, depending on how much ferric iron is formed, particularly into reservoirs like magnetite and into serpentine. And there's a ton of nuance in the mechanisms of those reactions and the conditions under which you really will and won't form hydrogen. And we'll only touch on some small parts of that today. a lot of the time in the interest of serpentinization or in discussions of serpentinization, there's a focus on the fact that to maximize the yield of molecular hydrogen that's generated, a lot of models, depending on how they're designed, will predict that you would get a maximum amount of hydrogen somewhere often around 300 degrees Celsius. And that can vary, but you'll often then see a sharp decline in the yields of hydrogen as you go down to lower temperatures. And that has pushed a lot of interest towards hydrothermal systems, like along the off-axis on our mid-Atlantic ridge and in other systems in the seafloor where we have a lot of high temperature hydration of minerals such as olivine. This reaction written on the top of the slide is just one type of a serpentinization reaction. It's one of the simpler ones. It's just olivine with a composition similar to the most common composition of olivine on Earth, reacting with water, making serpentine, again, this brucite or hydroxide phase, magnetite, iron oxide. And in this reaction, which is being used to generate this curve that you're seeing here, really the yield of hydrogen is really closely linked and proportional to the amount of magnetite formed, because magnetite is being considered the dominant reservoir of ferric iron. And you get more magnetite production at high temperatures. Yep. And so when you look at this and we think, does this mean that a lot of low temperature systems should be hydrogen limited? The question is, what's really controlling that enormous drawdown in predicted hydrogen yield? And the key phase that is in these models that drives this prediction is the one that I have a box around. It's the fact that there's these minerals, these hydroxide phases that end up being a big reservoir of iron, mostly in the ferrous state. And so brucite can be ferroin, can have iron in it, and it's increasingly rich in iron too as temperature decreases. And essentially what happens is olivine hydrates and it produces a bunch of secondary minerals, and many of them are locking up iron in the iron 2 state. There's no redox chemistry, thus no hydrogen. And so if there's nothing else you remember about today's talk, one thing that I want to say that I found very exciting from both field, theory, and experiment now is that is not true. Systems are not always hydrogen limited. We can actually find sometimes very high millimolar concentrations of hydrogen produced in natural systems. And the question is then mechanistically, why and how? When will that happen and when won't it happen? And some of what Nick will talk about today will really build on that as well. So the key for a lot of the systems that I've been looking at in lab and in field has been the formation of the brucite that I've been talking about. It can variably substitute iron into its structure. And I call it metastable because there are conditions under which it forms. It's thermodynamically predicted to form, but as the water rock reactions progress or the aqueous chemistry of the system evolves, actually brucite can become unstable and it can be lost. And so it often forms and goes. And it's a turnover of iron 2 in its system. And if the transformation of brucite results in an iron oxidation reaction, that can very much affect electron transfer. And so in these two images here, one on the left is an image from the kinds of rocks that I've been studying that have undergone low temperature hydration, less than 100 degrees C in terrestrial environments. And when you look at these kinds of rocks and you do chemical imaging of them, you'll often see these islands of these bright colors here. That is brucite replacing the original mineral olivine, our initial source of iron. That brucite is actually can be up to sort of 28% iron. And so it really stands out as a reservoir of iron. And when we look at the chemical potentials of that brucite, depending on an exact chemical composition, it can really poise the system at low redox potentials, and it can be very labile for subsequent electron transfer. And so the concept is just that olivine is what we often think of in a planetary context as being the initial source term for hydrogen generation. And it is. We look at hydration of olivine and we form brucite, serpentine, and magnetite, and we do get hydrogen generation across a range of temperatures. But again, this brucite, depending on how much of it forms and how much iron, can actually be titrating, I guess, would might be the right word for this, exactly how much hydrogen is made at different points in time and space. And serpentinization tends to be what we call a multi-stage reaction. We don't just take a body of rock or a body of olivine, hydrate it, and expend it. It tends to be that we, through time, hydrate it, and often the reactions get arrested. It continues while water is present. If the hydrology changes, that will cease, but it can be reinitiated. And so a common effect is that we have stage 1, which builds up a lot of serpentine in these hydroxide phases. And then there's a phase 2 or 3 or 4, and it depends on the system in which you exactly study. And the outcome of that is that often you see the loss of particularly the brucite. So just in this image, just a kind of cartoon to show, like, here's serpentine brucite, and then we just convert. In one case, we finally convert it all into serpentine, a stable mineral. But that serpentine actually is no longer very iron 2 rich. It's actually quite ferric. And so what's happening is often that iron 2 bearing brucite can react. And one agent that does this in fluids is dissolved silica. And there's a lot of interest in the mechanisms of that, that can then produce a variety of different minerals. That's what we have to investigate in our systems. What is the new mineral that forms? What's its iron 2, iron 3 characteristics? And that information really gives us a lot of power to determine how much hydrogen yield is produced in a system. One of the things that I'm interested in that connects it also back to prebiotic chemistry and different environmental states that we might expect is brucite doesn't only react with water or only react with dissolved silica. It can also be reactive towards other dissolved species. And examples of that would be carbon dioxide, nitrates and nitrites, phosphate, etc. Not all of those are effective redox reactions. CO2 and phosphate have very low redox potentials, although they're very close to the brucite conversion, depending on what it makes, magnetite, green rust, etc. But there is a lot of work, I think, here to be done, and it's an area that we're invested in deeply in an experimental way, trying to examine the reactivity of these minerals that we find in nature that we believe have the potential to do electron transfer with these. And the importance then would be, well, what would be produced? Not only molecular hydrogen, but other reduced species in systems. One of them that we have worked on a lot is ammonia. You can also get things like formate. There's a diversity of reduced carbon and nitrogen species, and that's a complex sort of beast that we're only on the edges of in terms of how to run those experiments and characterize that. We've been exploring the potential for redox transformations of phosphorus. Those are quite challenging. And so I'll leave that there right now, just as a window that we're opening up. There's a good experimental basis to go forward in this realm. But the last idea I want to put on the table today in this brief presentation is how the field systems are informing some of our perspectives on these things. And I particularly work in systems that are, again, non-hydrothermal at the moment. And what's been interesting is to probe systems where they're rock dominated, huge volumes of rock types that have existed through Earth history that exist elsewhere in our system. So they're poising a system at a state that we think we should see again and again. They're modern, but rainwater is getting into them and rainwater percolates through, but the rainwater rapidly takes on characteristics dominated by its exchange with the minerals that are there. And so you make shallow or short residence time fluid types, and you make deep, very highly reacted alkaline, hyperalkaline fluid types that are present. But we've been able to go in using boreholes that existed and that we've drilled to probe different states of how the subsurface system structures itself. That's an image of Oman, which is just one place on Earth where you do get these massive exposures of ultramafic rocks that are looking like there's no water present in the system. It's dry, but all the water comes in and is stored in the subsurface. You only have to go meters below your feet to start to access it. And when you do, you don't have to go very deep to start getting very high hydrogen concentrations. So to make hydrogen feel more real, this is just hydrogen bubbling out. We're pumping fluids out of these boreholes. And when we do a profile in this particular one I'm showing here, we move rapidly at the surface to very low redox potentials, minus 750 millivolts that we're sitting at. We're also at pH 11, which is how we can be at such a low redox potential. And we're at temperatures that are below 40 degrees Celsius. And in these kinds of systems, there's a lot of potential to trace the recharge and discharge paths of fluids over varying residence times to understand how they evolve chemically along those flow paths. And in areas, we also can look at the mineralogy. And for example, we have rocks that are very abundant in this furrow and brucites and rocks where it reacts out. So we can look at how the mineralogy modulates the subsurface aqueous geochemistry. And I think, again, in this sort of prebiotic chemistry sense, it's a window to help us start thinking about how carbon, sulfur, nitrogen, phosphorus speciation is going to change across those mineralogical gradients. One example, and I'm just doing the inorganic chemistry here, is nitrate. So as I was saying, nitrate can be delivered into these systems from rainwater. It becomes the most abundant oxidant until it's fully consumed in these systems. Oxygen is just scrubbed out almost instantaneously. So as we move into the subsurface, we trace nitrate as our oxidant, and that's lost. And the interesting thing that's been very clear as we've moved across different borehole systems is that as nitrate disappears, as we get into these more reactive fluids, ammonia, it becomes a reservoir of nitrogen, and we have reduced nitrogen and ammonia as well as other dissolved organic nitrogen species that we're still characterizing. And so this change in the balance of nitrogen species and the potential here for all sorts of reactions, including reductive amination reactions, is of great interest to us at this time. So I think this is essentially almost the last slide. I want to accentuate again this idea, though, of how strong the chemical gradients are that get established in this relatively low temperature system over these spatial scales here of tens to hundreds of meters. So if you can see I'm pointing sort of at the bottom of this fluid system part of the diagram. There's a lot going on here. The main idea to let you know again is, fluids are often minus 600 millivolts or lower. They're rich in hydrogen at millimolar concentrations, high methane, we have high ammonia. And we can look at the mineralogy paired with that. And this is where we have these furrow and brucites, these hydroxide phases, and we even have native metal alloys loaded into these rocks that we can trace. And then we can move up and we have really sort of sharp redox and pH transitions that happen. We go 700 millivolts more positive. We go up 2 to 3 pH units. And we also start to see changed couples in the mineralogy and the types of nickel and iron oxide and sulfide phases that we find present. And again, we then move to a surface regime, which can be on the order of just 5 or 10 meters to maximum about 100, depending on the fracture densities. And that is a more surficial reacted fluid, more oxidizing, but not oxygen carrying. It's just a more oxidizing state of the system. And this transition we see repeated again and again. It's just the scale compresses and expands, and that's very much a function of the hydrology. And so to really start to understand the changes in chemical speciation of many of the components that we're interested in, it becomes a challenge of trying to understand where you are within not only a rock-hosted system, but how fluids move through it and what that hydrology looks like and where fluids mix. And we don't just go on a one-way path, reductive path. I think that's often been a concern. We have mixing zones. We transition to more reducing and flip back to the more oxidized state, depending on how fluids are discharged up towards the surface. And they mix in the shallow subsurface. And these are very interesting zones for both biology and the chemical dynamics that happen. And they also mix into a surface regime. And I think that is also going to be very important in the continued discussions of prebiotic chemistry, the subsurface-surface connection. And what are we really feeding in to these systems? What reservoir do we have here, but it's not inaccessible. It is connected to and communicating with the surface environment. And the last statement there too is just that I think we have the potential to understand these systems even in a prebiotic state. We just changed the atmospheric input. We need to think at those models of what's changing through impacts, as Paul said earlier, and through different temporal time windows. And they are communicating, though, into the system. They are not decoupled from each other. So with that, really the key points are you can get hydrogen-rich rock buffered fluids near surface conditions. Definitely can in hydrothermal, and we've known that, but we can in low temperature environment. There are several phases of interest that are reactive, labile for electron transfer, and are important in hydrogen generation or other redox reactions that we care about. It is not trivial to predict the timing and extent of hydrogen production. We have to understand more about the reactivity of the iron 2 bearing minerals with many dissolved species, like I was saying, and that's very experimental at this point. Many labs are trying to figure out how to tease out the controls on reactivity. But I think that as we keep improving this understanding of the mechanisms that control hydrogen generation, we're also going to effectively move into better understanding the potential for which transformations are feasible with nitrogen, phosphorus, carbon, and sulfur. So as a very broad sweep on that, that's sort of the main thing I wanted to put into the discussion for today.
Right.
Thanks.
Thank you so much. I think that's a wonderful start to the discussion, and it'll be a good segue into what Nick has to tell us about what may have gone on Mars and Earth. We do have some time for questions, and it looks like Ziwei has a question.
Yeah, thank you. I think it's a very interesting point to analyze the hydrogen production and the other reduction, because I just got a paper nearly accepted in some journal. It's just pending on the editor stuff. So in that system, I did carbon dioxide reduction combined with the hydrogen production, which all observed in NMR yield. So it's like a millimolar something. And I think Paul know a little bit of that work. And because on the surface, it's cannot avoid the UV radiation on the water or something else. And in my system, I have bisulfite carbon dioxide, just irradiation at a little bit basic condition like pH 9 something. And I see a lot of organic stuffs from fomate to even tartrate. It's like a C4 compound. And also the hydrogen production was observed, which like millimolar of yield. So the chemistry is fine. Just, the possibility of this system is a little bit questionable, but not so much, because UV radiation was proved by Paul's recent paper, Astrobiology 1, which is acceptable under prebiotic condition. And the sulfide is also a probiotic stuff which comes from the volcano eruption, and carbon dioxide as well. It's everywhere. So this is another possibility to have hydrogen and other reduction reactions. So yeah, I just want to raise up this interesting point to open discussion. Yeah. Thank you.
Yeah.
Thanks.
No, I mean, I think it's very important for you to bring. There's so many different pathways for producing hydrogen. And I think a lot of times the question comes back to how long you want that to persist for, and the potential other geochemical states of the system around you at that moment in time. You did mention CO2 reduction, and this is just a thorny problem in the field with a lot of, is that hydrogen production is facile under numerous conditions. CO2 reduction is not. And so it's much more rare to find effective ways to truly reduce CO2, even just to formate. But just getting that first step to formate, and let alone to other complex organic compounds. And that I think remains a major challenge in the field, is understanding when that is feasible in a persistent geologic context.
Great. We have another question from Barb.
Actually, I just wanted to echo what Alexis was saying. I think one of the major outcomes from today's talk will be this whole issue that the feed through into the carbon cycle is really one of the next horizons and challenges for all of us, and is amenable for investigation on all kinds of levels. But I think Alexis and the previous person who posed the question have really nailed one of the burning issues. How do we feed this through to understand the deep carbon cycle?
Great. I very much agree. And I imagine that future discussion will probably touch on that. So let's now turn to Nick, who will be telling us a little bit about a possible source of hydrogen on Mars and on Earth as well, potentially.
Okay, great. Can you all hear me and see my slides?
Yes.
Okay, thanks. Our interest in hydrogen is relatively recent and started with basically with the MSL rover, which ended up landing at the surface of Mars some years ago in 2012. And really, when that rover started analyzing a succession of mudstones and sandstones preserved on the surface of Mars. And that I guess the way into hydrogen here is not so obvious, but these mudstones and sandstones, look and sort of are composed of many of the same components that mudstones and sandstones could potentially be composed of on the Earth. But those components are a little bit different in that they're composed mainly of mafic materials, so materials rich in iron and magnesium. But these figures here just summarize some of the basic characteristics of the mudstone succession that the MSO rover has been working on. So this is several years worth of work starting in 2012. But what's important about this succession of mudstones is a couple of things. One is that they're so ancient. The estimates are that these mudstones were deposited about 3.6 to 3.7 billion years ago. And this is one of the principal reasons why Mars exploration is so fascinating, because Mars essentially preserves what we think is an extensive sedimentary record right at its very surface, whereas on Earth, most of those rocks have long ago been obliterated. And so if one can get a rover to the surface of Mars and be wise in picking an outcrop or a succession that can constrain paleo environments, then you can come up with a series of observational constraints on what early planetary environments might have been like. And so I'm just going to talk about a few of those constraints and a geochemical system associated with these mudstones that we believe produced hydrogen. So aside from their age, the rocks we believe were deposited in a shallow lake environment from an alluvial fan. And as those sediments were deposited in the lake, they were composed of basaltic mud, so the minerals that compose the igneous rock: basalt, olivines, pyroxenes, and plagioclase. A fair complement of clay, iron and magnesium rich varieties. There are some iron sulfide minerals, which are believed to be detrital in origin, so physically deposited, not chemically formed within the sediments. And then abundant magnetite. And the magnetite, on the other hand, in comparison to the iron sulfides, is thought to be authigenic in origin. So it's thought to have formed during or shortly after the physical sedimentation of those materials. And this really sparked our interest because for all we know about the system, we're dealing with a relatively low temperature sedimentary system that is really based in a fluvio-lacustrine environment. And so if the magnetite is authigenic, if it's actually crystallizing in association with these sediments and the chemical environment that's surrounding them, what are the reactions that's producing that magnetite, and could it be in some way linked to interesting redox properties? On the right-hand side is a summary diagram of the mineralogy and how the mineralogy varies across different drill sites. And so you can think of this as sort of a spatially resolved pattern in mineralogy. But what's important here is the bottom figure that has the color coding on it. You can see the magnetite actually increases in proportion from the left-hand diagram to the right-hand diagram. In some cases, it almost doubles. And that's important because the drill holes on the right-hand side are the holes that are thought to represent the interior of the lake. So moving away from the sediment source and into the relatively deeper portions of the lake, or the middle portion of the lake. And aside from increasing magnetite, it is almost always the case that silica is also associated with that magnetite in the form of opal CT, which is sort of a disordered form of silica. And so in terms of the the depositional environment, this is nicely summarized by Joel Hurwitz in a paper in 2017. But what this diagram shows is it shows that the spatial variation in mineralogy, and then it sort of hypothesizes how the geochemistry of the lake might be evolving in space and time. And so the idea here is that this lake, the lake environment captured or redox stratified environment, where the deeper waters are somehow reflecting or associated with reducing environments. So that is reduced compounds are more abundant than oxidizing compounds. And then the surface portions of the lake, or the shallower portions, are associated with more oxidizing or oxidized materials and oxidizing conditions. And so that lateral variation in the mineralogy, combined with the sedimentology and the stratigraphy that really gives us the physical environment, was the basis for this hypothesis that the lake environment itself was redox stratified. So this is a really interesting sort of a framework to further investigate some of these hydrogen producing reactions. And you can see outlined in this diagram here that the magnetite silica facies, or the set of sediments that share these characteristics, are associated with the deeper, more central portions of the lake. So we were asking at this time, how did this mineral assemblage form? So how did the magnetite end up there, and how did it end up where it ended up? So why is it only associated with the deeper portions of the lake, or the center of the lake? And what is that telling us about water chemistry and the conditions, both physical and chemical, that are acting on these sediments? So in order to make some headway on that, over the last few years, we've been understanding the nucleation and growth kinetics of ferrous iron bearing minerals. And it's somewhat surprising to know that we still don't really have as good of a grasp on the growth kinetics and phase transformations among ferrous iron bearing materials at relatively low temperature. And part of the reasons are they're not as well studied as some of the other minerals that are more common in low temperature systems. But then another reason is potentially that they're a little bit more difficult to study because they require oxygen-free environments. In any case, the experiments that we're conducting as part of this study sought to examine or map out the parameter space that might be associated with the waters that were bathing these sediments. And we know that those waters were derived from basaltic materials, and so therefore the waters in a basic way had to contain ferrous iron, magnesium, silica, and potentially other cations like calcium and potassium and sodium. We decided to include as variables in these experiments dissolved inorganic carbon and alkalinity and pH. And basically what we're doing with these waters is looking at chemical variation in waters that could be produced from a basaltic substrate, and then looking at the nucleation and growth kinetics of the minerals that are derived from those waters as a function of pH. And so a lot of these experiments were run in reaction vessels at zero oxygen conditions at constant pH to try to map out the kinetic behavior of mineral formation in these environments. But what these photos are showing here is that in some experiments, we ended up with basically reaction vessels filled with magnetite rather quickly. So we end up wrapping these vessels in foil because we're worried about the effects of photooxidation from the light sources around us. But in a matter of hours, under the right conditions, you actually end up with quite a bit of magnetite floating in the reaction vessel, which of course was interesting and relevant from the standpoint of the ancient sedimentary rocks that I just talked about. So it took us a little while to figure out that the magnetite was actually forming through a couple of different mineral precursors. And so these are powder X-ray diffraction profiles of some of the solids that were generated over the course of the experiments. And you can see at the bottom of the panel here that the first solid that ends up being formed in some of these experiments is something that Alexis had discussed in the previous talk, and it referred to as ferro and brucite. This is the iron end member of the ferro and brucite, or just FeOH2. Sometimes it's called white rust. I don't think it has mineral status because I'm not sure it's ever been found naturally on Earth's surface. But in any case, that material is around and it very quickly vanishes. And then we end up forming green rust, which is a mixed valence iron oxide material. And then after a couple of days or so, we're left only with magnetite. So this is a really interesting sequence of mineral transformations. And what's happening here is that the initial precipitate that forms from the waters is FeOH2, which forms at relatively highish pHs, as Alexis pointed out in her talk, pHs of about 8 and higher. But what's happening is that as the FeOH2 ages under those conditions, a relatively alkaline pH, the ferrous iron that's trapped in those solids is desperate to shuttle electrons off to H2O. And so in so doing, oxidizes itself, produces hydrogen as a byproduct, but then also produces Fe3 plus in amongst those octahedral sheets. And of course, that leads to an ion charge imbalance, which has to be satisfied by interlayer ions. And so we end up forming a variety of green rust phases. Now, green rust is metastable with respect to magnetite. And so over a couple of days or so, we believe that the green rust is transforming to magnetite, not through a solid state transformation, but a dissolution reprecipitation transformation, simply due to its thermodynamic metastability with respect to magnetite. So this is a really interesting mechanism and has the potential to produce rather large quantities of hydrogen. And in fact, we observed that some micromole concentrations of H2 were produced in these experiments. So not quite the stoichiometric amount of hydrogen that we were expecting in some cases, but we chalked that up to a variety of different reasons. And loss processes associated with the way that we were running the experiments and sampling for the hydrogen analysis. So this is really exciting, but one of the things that we're concerned with, at least in applying these experimental results to the early surface of Mars and potentially even the Earth, is CO2. So if it's the case that you're forming a ferrous iron phase, what about CO2? Wouldn't the presence of CO2 basically short circuit this process and end up sequestering most of the ferrous iron as iron carbonate? And the answer to this question sort of surprised us. We ended up repeating a lot of these experiments in the presence of very high concentrations of dissolved inorganic carbon that essentially equivalent to waters in the presence of a 1 bar CO2 atmosphere. And it turns out you have to be really highly supersaturated to start nucleating iron carbonate from solution. And so because of that, that nucleation barrier, you still end up producing a lot of FeOH2 in any case. And so these are some experimental data that kind of map out that dependence. So the FeOH2 precipitation as a function of pH and CO2. So the black line indicates thermodynamically where siderite, the ferrous iron carbonate, should form, and the red line actually maps out kinetically where it does end up forming or where it does nucleate, orders of magnitude higher in terms of, in this case, CO2 fugacity or higher pH. And in the intermediate space, once we're supersaturated with respect to FeOH2, which is the dashed blue line under these conditions, anything to the right of that ends up eventually producing green rust and through the FeOH2 process that I mentioned in previous slides. So this is quite interesting because it identifies a potential mechanism by which the magnetite could have formed in these sediments. But the question is, why is the magnetite associated spatially in the way that it is? So why is the magnetite only associated with sediments that are deepest or in the central portions of the lacustrine deposit? And I guess the question we had that we thought could help us answer that was, could groundwater infiltration play a role rather than just the surface water feeding the lake? Could groundwater sources be a component here? And this actually turns out to be relevant in the case of Gale Crater, the depot center where these sediments are being deposited, because it ends up being the deepest hole on the surface of Mars for thousands of kilometers in any direction. So just a simple treatment of the groundwater hydrology predicts that if the groundwater table is going to rise, the first place that's going to feel that is going to be Gale Crater. So the last component of this was testing this hypothesis using a set of reactive transport calculations. And so basically what we're doing is we're using a 3D grid, and we're predicting what's going to happen if groundwater infiltrates up to the bottom of the sediments and actually meets lake water. And so we had to prescribe some chemical compositions associated with both groundwater and lake bottom water. But the groundwater, the chemical composition of the groundwater that percolates through basaltic lithologies is actually quite well known from studies based on Earth. So there's been a lot of groundwater hydrology and geochemistry work that's been done in mafic and ultramafic lithologies, as Alexis talked about, and places like Iceland as well. But one of the take-home points is that the characteristics of these waters end up being that the waters are relatively alkaline, so they've got high pH. Most of the CO2 has been scrubbed out because that's been precipitated as carbonate phases. And so you end up with these waters that don't really carry much iron. They're alkaline and anoxic because the oxygen's been scrubbed out as well, and don't really have much CO2. In contrast, we had thought that because the lake system was so shallow, that the possibility of higher CO2 might have actually led to lake waters that were relatively rich in dissolved inorganic carbon, and therefore could have supported a higher complement of ferrous iron. And so on the right-hand side of the diagram here, what this simulation is showing is mixing those two different waters, those chemically distinct waters. And essentially what you end up doing is you end up titrating the ferrous iron out of the lake water using the alkaline groundwater. And so the FeOH2 is predicted to form right at that mixing interface. And we even included a stoichiometric relationship associated with green rusted magnetite to estimate just how much hydrogen we could produce under those circumstances. And the answer is you produce a lot. And in fact, you produce so much that it ends up becoming a free gas phase in the sediments and producing bubbles. And then funny enough, there are concretions within those sediments that are thought to have been gas-filled bubbles. And the size distribution of the bubbles as measured from MSL images actually corresponds with the amount of hydrogen that you could produce in this reaction using the abundance of magnetite. So it's entirely plausible that those bubbles could have been formed from hydrogen associated with this mixing zone process, which is kind of a neat conclusion. So we think that groundwater infiltration was important here, and it's really the combination of these two distinct fluid types that allows you to form FeOH2 and end up producing the hydrogen and eventually magnetite. But of course, not the iron carbonate, because the other thing that you're doing in this system is you're diluting the dissolved inorganic carbon that's coming in from the lake water. So it ends up being a fortuitous set of geochemical circumstances. And so this is just a diagram of the right-hand side, just plotting what's happening as a function of time in the center of the domain. And so eventually you form more magnetite at the expense of the most reactive mineral, olivine, in these conditions, and producing a fair amount of hydrogen. So I'll just tie up here and entertain some broader implications. I think this process is potentially applicable to other planetary surfaces and even the early Earth environments, because effectively what we're looking at is we're looking at fluid mixing between two different fluid types. One is a high CO2, potentially iron-rich, ferrous iron-rich surface water, and the other is an anoxic CO2 and iron poor alkaline groundwater. And so this mixing interface and the dynamics of that interface probably allowed you to form phases such as FeOH2 or ferrin brucite as Alexis had talked about earlier, and triggering that hydrogen production and magnetite formation process. And we even kind of took the extra step and really, kind of stuck our neck out and did some back of the envelope calculations to estimate just how globally important this process might have been in the early surface of Mars. To do that, you have to take into account global groundwater hydrology, for which data actually exists or at least simulations actually exist for the early surface of Mars based on geophysical constraints. And we had estimated that if this process was occurring over small percentages of the surface, so say 0.1% of the surface or 1%, based on maximum areas where groundwater infiltration could actually have occurred, then if this process was sustained over 10 to the 4 to 10 to the 5 years, you can actually produce enough hydrogen to start to become atmospherically meaningful. So, I mean, these are very, back of the envelope estimates of hydrogen production, but it suggests that that this sort of a process could be potentially important in from a global mass balance perspective. Any case, so I think I'll leave it there and entertain any questions. But thanks once again for inviting me to speak here, and yeah, looking forward to continuing the conversation.
Thank you so much, Nick. We do have time for some questions, and I'll start off with one. How does the CO2 fugacity relate to the partial pressure of carbon dioxide in the atmosphere? And how do your conclusions change if you don't have that sort of groundwater source? Do you really just get a whole bunch of carbonate, or is it still possible if the CO2, are the regions where the CO2 is still low enough, deeper in lakes, to still allow for this potential source of hydrogen?
Yeah, so I had plotted this, or I had showed some of the iron carbonate experimental data as a function of fugacity of CO2, which is sort of misleading because we're talking about waters, and so another way to display this would be as a function of dissolved inorganic carbon concentration, or something like. The assumption is that the groundwaters probably don't have much CO2, but that's only because of the assumptions that we used in looking at alkaline waters percolating through basaltic lithologies. I mean, in truth, they were probably associated with a whole range of different DIC contents, some of which probably gave you plenty of iron carbonate. So again, you need to be right in the geochemical window where I think you're not getting iron carbonate, but you're allowing things like FeOH2 to precipitate.
All right, thanks. Alexis has a question.
I mean, later I have tons of things I could ask you, Nick, but just listening to that too, it just reminds me again and again how important it'll be to start finding all those carbonates on Mars, and what flavors of carbonates and where they are localized. But when I've thought about your magnetite pathogenesis story, I often am just so interested in the mechanism of the transformations you were talking about today. And I haven't myself spent nearly as much time thinking about this groundwater component, deep groundwater component of the story you were just sharing, and how special Gale is, and the way you mentioned that it's one of the lowest points on Mars. So you kind of had the best test bed to see this phenomenon, it sounds like. So as someone who's not an expert in at all, and like, how many other places do you really think could have had a comparable chemistry to Gale in that way, like that would have accessed deep groundwaters and allowed this really important hydrological phenomenon to go forward?
Yeah, so that's a great question. I mean, there are larger regions of the planet that are associated with topography and I guess global mean elevation are about the same as Gale. So the Eridania Basin is another really big one that, again, associated with the aftermath of an impact. So the folks that have looked at global groundwater hydrology on Mars predict that if you end up with groundwater upwelling, you probably got a significant fraction of the surface where the groundwater is going to come up and actually meet the surface. And unsurprisingly, that fraction is dominated by the largest and deepest impacts. But I guess, I mean, this is all really back of the envelope stuff, and it's difficult to know, exactly how important this process was. Although one interesting observation comes from magnetic data. So magnetic anomalies, crustal magnetic anomalies, are actually associated with some of these areas. And I talked to Ben Weiss about this at MIT, whether those magnetic anomalies could potentially be reflecting higher proportions of magnetite, say, in the sediments, as opposed to any other post-impact processes that could result in magnetization. And he seemed to think it was totally possible, so, and kind of worth digging into the global magnetic data a little bit better to provide another constraint on, I guess, the process.
Yeah, that would be really, really interesting if you could connect those two. But the only other comment I'll make, which is just sort of a general one, is I think it's been fascinating. I found every year that I've been working, teaching, doing research, the more that hydrology has mattered in what we are understanding in the field system. And without understanding the residence times, the chemical reaction paths, the mixing domains and where those are localized, that's where all of the important chemistry is happening. And when you study subsurface biology, it then links directly into your abilities to actually find that. And so I didn't take hydrology, in my original training, and I definitely encourage students to do it now because it couples in so many different ways that I don't think people recognize till later.
Yeah, absolutely. I mean, I guess the upshot of this is that it's very much an interface process, right? I mean, that's where all the action is occurring.
All right. So the comment about the importance of hydrology, I think, will feed in well when we shift a bit from serpentinization into talking about another known source of abiotic hydrogen on Earth, which is radiolysis in deep waters. And so, Barb, if you would, if you're ready
the
to
share
talk with us.
screen. Do you get the share screen? Are you seeing the slides? No?
No, we are not seeing
Okay,
the
let me
slides.
try again. I went to share screen.
Ah,
There.
something's happening.
Are we there now?
Yes, we aren't
Perfect.
quite, yeah, we aren't seeing the slideshow yet, but oh, great, we are now. Perfect.
Okay, great. Just a small time lag for some reason. I'm not sure entirely why, but it's just such a pleasure to be here today. It's such a dynamic group that you put together at Cambridge, and the opportunity to chat even virtually with Alexis and Nick is always such a pleasure. I want to thank you, in fact, too, for your comments here, because it's allowed a beautiful segue into the third component of this. I am a geologist by training, but specifically a hydrogeologist. And so this idea of follow the water is something that we do not just on Mars, but also on Earth. And you'll see the perspective of that water reflected throughout what I'll talk about today, which indeed is going to accept everything that's been said about serpentinization. We work on that too. And serpentinization takes place in all of the systems I'm going to show you today. But given that I had Alexis and Nick already talking about that aspect, I chose particularly to focus on the other aspect of hydrogen production within these systems, which is indeed radiolysis. So what I'll do is a quick outline, again, additional perspective on hydrogen production from radiolysis. And indeed, I will also be focusing primarily where we work, which are in analog environments, deep groundwaters, in the deep terrestrial Precambrian crust. And here too, I really owe Nick. I think he's really given us the reason for why have I spent 30 years of my life deep in these rocks underground? Well, it's that although many of the ancient rocks on our planet, as Nick mentioned, have been reworked, certainly not all. More than 70% of the continental crust is Precambrian in age, and vast swaths of it are between 2.5 and 3.8 billion years. So there's been a lot of destruction, but if you live on those rocks and you know it can take you several days to drive across them, you realize there's still a lot of billion-year-old real estate on this planet. And it provides, particularly if one can enter the subsurface, it provides a perfect analog environment for investigating what these deep groundwaters might be like within a planet like Mars. And so this gives you a picture of what that looks like. This is indeed about, this one is about 1.8 kilometers below surface, but we work everywhere from surface right on down to 3 and 4 kilometers depth. What you're seeing is a natural phenomenon. These are saline groundwaters trapped within these rocks that naturally discharge. And then if you go in and you put in this case, an underground laboratory, an underground mine, then obviously you increase the rates at which these fluids are released, but it's nonetheless a natural phenomenon. And interestingly enough, miners throughout the world, whether you're in South Africa or Finland or Australia or Canada, they've known about this for over 100 years, but it was something that just ran underneath the radar of the scientific community. On the right-hand side, you can see a demonstration. I didn't want to try and put in a video in case it glitched, but you can see all of these bubbles, and that is active exsolution of a gas phase that can be up to 50% hydrogen, depending on where you are on the planet. So it gives you a sense of very similar to the kinds of things that Alexis is talking about in an ophiolite environment. But rather than having that sort of scale be 0 to 400 meters, here we're really looking at 0 to 4 kilometers as a spectrum. Again, I'll speak, people are working on this all over the world. Our own particular group, I've worked primarily in Canada, South Africa, and Fennoscandia, and a big aspect of what we've looked at is not just the geochemistry of these fluids, but also, as the others have mentioned, the real link between the geochemistry of these fluids and deep subsurface microbiology and habitability. I'm a noble gas geochemist as well, so we couldn't resist also adding in the time scale aspect, and in particular, understanding the residence times of these fluids. And in a number of studies through the years, we've been able to show that the residence times of these fluids also provide us with a beautiful gradient or spectrum, because you can actually look at fluids that range in age from ones like Alexis mentioned, where there's still a very active connection to the surface, to others that have been isolated on thousands to millions, and in a few special places, even more than a billion-year timescale. So it allows us to look at that whole spectrum of waters that are still in connection to the surface to those that have really been isolated on long time scales. And again, that hydrogeologic isolation really speaks to some important aspects here, because really what it means is that these ancient rocks and ancient fluids give us the opportunity to go into hydrogeologically very tight systems. Imagine the very bottom of Nick's scale and the very bottom of Alexis's scale. And these are places where, because the hydrogeology in these fractures are so hydrogeologically tight, the products of water rock reaction can actually accumulate on long time scales, even if the rates of reactions are slow, even if the temperatures are low, as they are in these tectonically quiescent systems. But we have just the evidence in front of us all over the world. These are, like the hydrothermal vents, some of the most hydrogen-rich environments on the planet, with concentrations in the dissolved of up to 5 to 15 millimolar. And again, like in the picture I showed you earlier, that translates to anywhere from a few percent to up to 50% of the gas phase made up of H2. In 2014, we went around the world and tried to pull together data from our own work and others, just demonstrating the distribution of that hydrogen in many of these systems around the world, including a few of the ophiolites, the Samal ophiolite, similar to what Alexis talked about, but mostly focusing indeed, as shown in green and blue, on the Precambrian crust. In other words, the ancient rocks of the planet that make up 70% of the continental lithosphere. I've inserted just up here a quick picture of the Canadian Shield, shown here in blue, and that same section shown here, just to point out again that I take it absolutely, the serpentinization is a huge component of hydrogen production in these areas. These swaths in black are the famous greenstone belts, 2.5 to 2.7 billion year old ultramafic rocks of the Canadian Shield. They're some of the largest exposures of ultramafic rocks in the history of Earth. And indeed, hydrogen within those rocks was a no-brainer. It wasn't necessarily surprising for us to find it there back in the 80s when we first started doing that work. But what I'm going to focus on today is take that serpentinization as a given and focus instead on something that presented a bit more of a problem, which is when we moved in about 1995 with T.C. Onstad and Esther van Heerden and others to take a look at these systems in South Africa. There are many ultramafics in South Africa, but they didn't happen to be within the particular settings within the Witwatersrand Basin that we were working with. There wasn't ultramafics there, so hydrogen wasn't necessarily expected to be as high. And yet, as you can see from the distributions, we're also seeing hydrogen levels on the order of 1, 2, 3, 10%. And so finding all of that hydrogen required us to look a little deeper because it wasn't obvious that serpentinization could be the sole source within that geological setting. We had to go way back. And in fact, what's interesting is if you take a look at Marie Curie's 1910 treatise on radioactivity, what's fascinating about it is it deals not only with the definition of radioactivity, but there's entire chapters on sets of experiments where they were looking on the effects of what at that time they simply called émanation radioactive. That is alpha, whoop, look at that, my accent moved, oh well. We now know, of course, that these are alpha, beta, and gamma particles. But what they were looking at then are not just the radioactivity of uranium, thorium, and radium, but they were looking also at radiogenic reactions. That is the effects of alpha, beta, and gamma particles on other gases, liquids, and solids. And this is one of the first places where she's citing the Geisel experiments demonstrating radiolytic decomposition of liquid water to produce hydrogen and oxygen. So the investigations of this go way, way back to the earliest part of the nuclear chemistry era. And indeed, Lee Hung Lin, working at Princeton, but also with us at the University of Toronto in 2005, did a whole series of studies looking at modeling, field, and theory, and demonstrating that the hydrogen within these more felsic settings of the Witwatersrand Basin was in fact attributable not so much to serpentinization, but in that mineralogical setting, more to the effects of radiolysis. And in fact, this radiolytic decomposition of water taking place in a natural setting. And when we eventually, by 2014, did some calculations to try to calculate production rates and flux out of these systems, we're able to show that if you took a look at all of these sites around the world, looking at both radiolysis and serpentinization, that in fact you just about doubled our estimates of the global production of hydrogen. Prior to that, these kinds of estimates had been done from the marine crust, but the continents had been forgotten. And in fact, due to that, we were missing about half of the amount of hydrogen that we think may be produced on this Earth. Important both with respect then to subsurface biosphere now, but also important as we begin to think about the importance of these reactions for prebiotic chemistry before life arose. Hydrogen isn't the end of the story. One of the other interesting aspects is if you take a look at radiolysis, you'll see that there's been some beautiful studies done taking a look at these rocks, and in particular taking a look at not just the production of hydrogen, but the other side of the radiochemistry, of course, the fact that you're producing all of these short-lived radicals. And a number of studies had done some experimental work discovering that when you do have this radiolytic decomposition of water, you produce hydrogen, but all of these reactive oxide then can also attack solid materials, in particular sulfide minerals, pyrite, pyrrhotite, basically commonly known as fool's gold. And many of these systems that we're investigating around the world are in fact, as Alexis mentioned in her setting, places that are iron rich or iron sulfide rich. And so what we discovered here is that in fact, the dissolved sulfate in these fluids was also being produced by radiolysis. Very low levels of dissolved sulfate deep within the earth, but they're directly related to this indirect radiolytical oxidation of the pyrite. And the evidence for that actually came from the sulfur isotope data. I won't spend a lot of time on that now. I can refer you to the Lee et al. Paper. Long Lee was a postdoc at Toronto when he did this work. Essentially, I'll just show you here this one particularly important parameter, the CAP33 sulfur isotope signature, is very diagnostic of sulfide minerals from this point in Earth's age, about 2.5 billion years. And as you can see, the dissolved sulfate maps directly onto that. It was one of the key things showing us that we had this direct link between the dissolved sulfate in the water and the solid minerals. In addition, though, if you look at the x-axis, you'll see in this other important sulfur isotopes that the waters were offset with respect to this. And again, that's consistent with what could be expected from the indirect radiolytic oxidation of pyrite. And so what's interesting about this is that this system showed us that all in all, you actually had radiolysis providing the whole closed loop, a coherent long-term mechanism capable of supplying both the electron donor and the electron acceptor, and thereby an answer to how it is you could sustain microbiology in such isolated systems that might be, in fact, almost the opposite of what Nick and Alexis are looking at, places where the level of mixing is taking place on a much slower scale, both spatially and temporally. And that's not the end of the story. And what I want to talk about just quickly then at the end is just the most recent work we've done, extending this to take a look at the carbon cycle as well. For this, I'll focus in particular at this one site. We've worked at dozens around the world, but this one's quite special. This is an ancient hydrothermal deposit of 2.7 billion years in age on the Canadian Shield. It's one of the most well-preserved in the world, and we've been working there through the years from the time that they were about here, about 1.5 kilometers below Earth, to where they are now, which is drilling and expanding at about 3 to 4 kilometers below the surface. Some of the early studies going right back to my PhD were actually on the abiotic organic synthesis within these fluids, in particular the abiotic production of methane and hydrogen from serpentinization, but coupling that hydrogen from serpentinization to the production of methane through abiotic processes. And so just recently, we were able to extend that a little bit further, largely because of the effects of radiolysis. And so just this year, we published a study looking not just at the methane, ethane, propane, and butane, but at acetate and formate, particularly from these fluids 2.4 to 3 kilometers below surface. One of the key things to remember about these rocks is they're not carbon poor. They're certainly poor in what you would call labile organic carbon, the type of thing that's easily converted by microbiology, but they're nonetheless rich in carbon and graphitic horizons, a lot of carbonate fracture minerals. What's dissolved in the water is somewhat less. The DIC is typically fairly low. The DOC as well, and I'll show you the specifics in a moment. But what's fascinating about the dissolved organic carbon at Kidd Creek is that, as I like to say, it reveals an unusual and very simple organic soup. Over here, you see in orange the total DIC for these fluids, and then in blue, acetate plus formate. So it shows you that for many of these fluids, acetate and formate are essentially the entire dissolved organic carbon load, or at least the very largest component. It's isotopically mass balancing as well. So showing us that DOC ranges from 2 to 5 millimolar, but what's really fascinating is acetate and formate alone make up 50 to 90% of that. Concentrations of acetate then at 1200 to 1900 micromole are amongst the highest ever reported in these kinds of systems, and the concentrations of formate equally high. So we tackled this working with Kai Heinrichs and Verena Hora at Bremen, because they're experts in the isotopic analysis of these two compounds. And essentially what we found is that these acetate and formate in these kinds of brines, in sedimentary, in continental crystalline rock, are very different from sedimentary basin brines. Sedimentary basin brines typically we have found that these things have much higher levels of formate. Formate is rarely found in sedimentary basin brines, whereas sedimentary basin brines often have many other organics, propionate, butyrate, oxalate. To date, we haven't found much of those in these systems, but they may be below detection limit. Kidd Creek also differs from the hydrothermal vents in one very significant way. The hydrothermal vents typically have much more higher levels of formate than acetate, often on a 10-to-1 ratio. These are flipped. Here, acetate is always dominant, typically acetate to formate in a 2-to-1 ratio. We've been able to monitor these for over 10 years and found no change in either the concentrations or the carbon isotopic compositions of acetate and formate. Something that's suggestive that there isn't a lot of cycling going on. The pool is fairly static. And these are some of the things that got us thinking about the possibility of abiotic chemistry. Again, just to show you a few of the more unusual features in these, this is a compilation from Verena Hauer of the distribution of acetate that she's done throughout the world. And you can see that the Kidd Creek systems are not only amongst the highest concentrations of acetate, but definitely the most enriched that she's ever measured. So these are unusual systems, high in concentrations of acetate and formate, predominance of acetate over formate, very highly enriched values for acetate, unprecedented in the literature, and different from other subsurface sites as well, although I can come back to that later if you'd like to. I'll go into the details of that one later. In the interest of time, I'll probably move on. The key thing was, with that many unusual characteristics, what we needed to do is certainly look at a larger spectrum of possible reactions to account for this. And working with Bénédicte Menez in particular and some of our French colleagues, what has been really helpful to us is taking a look at some of the physical chemistry literature that's being done, in particular experiments done by people looking at the nuclear side of things, nuclear waste disposal, et cetera. Because in fact, they've been doing a whole series of experiments that we as geochemists have not necessarily taken on board yet. And there's a wealth of valuable information and work going on there. This particular paper was demonstrating that radiolysis can produce not just hydrogen, but acetate and formate. And in particular, in a key set of experiments, what they showed is that the key to producing acetate, formate, and indeed oxalate was the presence of calcium carbonate. A lot of work still needs to be done to elucidate the details of these reactions, but I think it's a fascinating area for all of us to be paying attention to and to perhaps design some experiments around to understand really what the full spectrum of radiolytic reactions are. In our own case, it certainly allowed us a way to explain what we were seeing within these systems. In other words, not only radiolysis decomposing the water molecule to produce hydrogen, producing the oxides that by reacting with the sulfide minerals produce sulfate, but also reacting with all of the calcium carbonate lining those fractures likely to produce the acetate and formate that we're seeing. We have estimates of radiolytic hydrogen production around the world. Those are from Lin et al. 2005, which I showed you earlier. From the experiments from the phys chemistry literature, they too have production rates. And so we can link those and come up with estimates of acetate and formate production within our setting, back of the envelope anyway. And then we can take a look at those residence times that I interested early on. Given the various residence times for these different systems, from thousands to millions to billions of years, how much acetate and formate would we expect to be produced by radiolysis? And what's interesting is that at least at a very first order mass balance level, it can actually account for the concentrations we see. The Kidd Creek system is where we see the very highest concentrations of acetate and formate. That's also where we have the very longest residence times. I just jump quickly to one place, to the WITS. There we see residence times that are lower, on the order of tens of millions of years, and there we see about an order of magnitude less acetate and formate. So at least on a first order, it does seem to provide a mechanism to account for the concentrations of acetate and formate that we see in these fluids. And so just to close off then with some of the thoughts and questions around this, it's showing us that radiolysis is a much richer set of reactions. Radiolytic chemistry can not only give us insight into hydrogen, sulfur, and carbon, but may indeed be key to providing a mechanism for sustaining deep subsurface microbes in the absence of interaction with the surface photosphere. In other words, what might be happening below the systems that Alexis was talking about, where you actually get mixing. And potentially then a window into the prebiotic earth. Maybe we should be thinking about what my colleague T.C. Onstadt likes to call a warm little fracture, in addition to Darwin's warm little pond. And then in addition, in context of planetary habitability, this may provide some models to think about in terms of how chemolithotrophic life might be sustained on planets where perhaps photosynthesis never evolved. Future directions then, as I mentioned, lots of experiments needed to probe the reactions, the rates, the preservations, and foremost, the fractionation factors. Almost nothing is known about the isotopic fractionation factors associated with radiolytic processes yet. Minefield for us to plumb. There is a lot of very interesting modeling going on, including some of these papers that, in fact, Paul brought to my attention, Pastorak and Adam. We've actually got Ruta Karolite, who is working with myself and Chris Ballantyne at Oxford, have actually submitted a paper looking at the potential that hydrogen, helium, and nitrogen may be produced by radiolysis at some of our sites. One of the interesting things about radiolysis is that it is less mineralogically restricted compared to serpentinization. in that sense then, because uranium, potassium, and thorium is in all rocks, it may be a more universal driver of habitability, even if it, compared to serpentinization, might be a slower rate and process. And then finally, working with Jesse Tarnas and Jack Mustard at Brown, obviously we're translating some of these models to Mars, and been in touch with Nick and Ben about discussing some of these. And as well, if you'll take a look in the literature, you'll see there's a lot of interest in this idea of radiolytic contributions to what's being observed in Enceladus and Europa. So I think there's a lot of we're just on the cusp, I think, of a really explosive area of exciting research on this idea of radiolysis that I'm sure would make Marie Curie smile, because I don't believe they ever thought about it in the context of global habitability. And with that, I'm happy to lead into the discussion.
Wonderful. Thank you so much, Barb. It's very, very
That's
interesting.
just the acknowledgement slides for our group.
Wonderful. We do have some time for, Ziwei has a question.
Yeah, thank you. I think it's a very, very interesting talk, and I really like it. So some small question, because I'm not an expert in the radiolysis. So I saw you use different source of the radiolysis, and is this depending on the source of it? Sorry, I clear myself. So does it matter is the alpha or beta or gamma irradiation can split the water, or you need a mixture of them, or something else?
It's a very important point. Absolutely, the experiments done today do show some variation particularly in the rates, depending on the nature of the radiation. And so, again, it's just very early days. Most of the work that's been done has been done in a laboratory setting for a different purpose, largely to understand, in many cases, the fate of nuclear waste disposal. And most of that's been done then by looking at very simplified systems, where they're looking at just alpha or just gamma. Our own work with Li Hung Lin in 2005 was done with gamma radiation, largely because that's what we had available to us as a source. So all of that, everything you raise, very important to take a look at, because the details of exactly what mixture of these various radiative sources results in different either rates or products is still, again, an area of fertile research. We don't know yet.
Okay, thank you. So the second question is, how about the pH for this deep water reservoir?
It depends on...
Sorry, yeah, it's depending on the pH, or the reaction will be different, or is similar at different pH?
Radiolysis?
Yeah.
Yeah, again, some of these have been done at one set of pHs, so some of them have been done at varying levels of pH. The pH controls are, again, still to be investigated to a great deal of depth. I can literally point to maybe a handful of experiments that have done this at this time, most of them that I referenced there. And so the whole spectrum of looking at pH, temperature, meteorology, rock to water ratios, all of these issues is going to need to be explored. And in addition, the whole preservation, because at some point, of course, some of these begin to form, in many cases, oxalate forms. And the question is it forming as a byproduct of the others? So the sequence of formation of these various low molecular weight carbon compounds is very interesting as well. Which ones are produced directly as products, and which ones may be produced as a byproduct of the earlier products? These are all the reaction pathways that still need to be investigated.
Okay, thank you. So another question is the radiolysis stronger in the deep earth, or is similar to on the surface? So the density.
Right. Radiolysis is just a function of essentially the distribution of radioactive components. And so it's going to vary with lithology for sure. But unlike serpentinization, you're going to find it across all kinds of lithologies, because every rock that we know of on this planet, or pretty close, every lithology anyway, has certain background levels of uranium, thorium, potassium. And that is the controlling feature, of course, in the background levels of radiation.
Okay, so another question is the radiolysis is a local phenomenon, or is a global, so it can happen anywhere on the Earth or Mars?
It's absolutely global, and that's why it's so interesting, right? Because it's just a function of the composition, the structure of the planet. If you have uranium, thorium, and potassium, you have radiolysis taking place.
Yeah, so another thing is, I think in the universe, there will be more strong radiolysis from the universe, like from the outer space. And is that one can do the similar thing to this one, or is this source definitely coming from the mantle, or it can also come from outer space?
Well, I think if you're referring to things like UV radiation on the surface, yes, absolutely. That's another spectrum of energy that needs to be taken a look at. But do bear in mind, there's nothing mantle derived about what I've just described.
Okay.
We're in fact working in systems that have very little mantle contribution in the present day. These are tectonically quiescent crystalline rock. What they are highly radiogenic. But again, the uranium, thorium, potassium is distributed throughout the rocks of the Earth. There's no direct link. You don't need mantle-derived activity to have this be an ongoing process. So it's one of the reasons why these rocks, even though they are the massive, ancient, like I say, some of these are 3.8 billion years old on Earth, as well as on Mars. This is a way that continuing energy can be cycled to habitability, even if you no longer have high temperature processes like mantle inputs, plate tectonics, or hydrothermal vents.
Okay, yeah, thank you very much.
That's one of the reasons it's, I think, really helping to sculpt our
Yeah.
sense of habitability models for the universe.
Yeah, thank you.
Thank you so much. And thank you for some very, very interesting questions, Ziwei. There is one aspect that I think would change, which would be with the age of the Earth. The amount of radiolysis that you would have would change. And this is where I'd like to bring in also the other panelists to comment and put an input, because Nick's talk certainly the amount of hydrogen that would be released and the time in which it would be released would be very age dependent, and serpentinization would probably be very, very different, or the way in which these sorts of gases and rainwaters get incorporated into the rocks are very different if the atmosphere is very different. So I'd be very, very interested to hear both what you think the sort of most important changes might have been when you start moving back to the sort of early Earth, and when the sort of early life and prebiotic chemistry becomes relevant, and then also how you see the potential of investigating this either experimentally, or maybe in Barb's case, even there are some hints in the rock record because the rocks get so old. And Alexis, I saw that you had your hand up. Oh, okay. Cool. So I'd be really, really interested in both what you think might have been different and how we might be able to know.
Well, I'll do the easy one, and that because that makes Nick do the tough one. I mean, the easy thing we tend to say is that back in the early parts of Earth's history, things were an order of magnitude higher because of decay over time, right?
Yeah.
So the easy thing to say is, okay, uranium, thorium would have been 10 times higher at the beginning of Earth's time, minimum, higher heat flux, et cetera. All of this would mean more radiolysis in the early time periods, more serpentinization in the early time periods. But I've actually also am aware of people who have looked at it a little bit differently and suggested that might not be the case. So I want to just open up, having grabbed the easy answer, I'll open up the tough part to Alexis and Nick.
Nick, I was going to let you jump on that first, just because you've recently published on that idea of like what really would happen with hydrogen generation or not in early Earth condition.
Yeah, well, I guess our sorry, I had my cursor over it and didn't really need to raise my hand here. Yeah, we sort of chipped in on the part of the discussion of how would serpentinization potentially be different earlier on. But I guess, Barb, related to your talk, I was interested in some of the last things you just said in terms of extrapolating back to the composition of early crustal lithologies and estimating heat flux and how heat's partitioned through the crust. I mean, those are important factors. But just the simple observation that you've just got more more decaying species around, presumably acts in your favor. But have you guys tried to quantify this any further, or have you kind of been focused on other areas?
Yeah, not so much going back in time yet, because I'm looking really, looking at some of the work that you've been doing has really shown us that we need to take a very thoughtful approach to that. So I'd love it if you take a minute to tell folks about that work, because I think it's important that we recognize that although you can do sort of, as I mentioned, sort of back of the envelope estimates, that it all ought to have been better, faster, stronger. I think your work actually takes a much more sophisticated approach to that. And so I'd love to open the door to give you a moment to talk about that one.
Well, sure. This is work that was led by Ben Tutelo, who's a geochemist at the University of Calgary. And this started as a sort of an idea that we had when Ben was a postdoc in our group. And actually this relates to most of the things that Alexis introduced in her talk, which is understanding the mechanisms underpinning hydrogen generation during serpentinization, and specifically iron partitions from rock forming silicates to some of the other iron rich phases that are associated with serpentinization. But we were asking the question, how much hydrogen could be produced from off axis or lower temperature serpentinization earlier in Earth's history. And Ben was working on trying to nail down the mechanism by which iron serpentine is formed as part of serpentinization. So, my understanding is that magnetite is a common byproduct at relatively higher temperatures, so maybe 200 degrees C and higher in serpentinizing systems. But iron-rich serpentine is a common product in the lower temperature systems and can account for quite a bit of iron partitioning. And it's been linked to hydrogen formation. And so what Ben ended up doing in this work is placing some constraints on the mechanism by which iron-rich serpentine forms in association with serpentinization and how much hydrogen it produces. And the observation that came out of this, and this is supported by laboratory experiments and new thermodynamic models that Ben has put together, is that the mechanism by which you generate hydrogen in low temperature systems, and you need the iron-rich serpentine to do that, is controlled by the silica activity or the silica concentration of the silica activity controls what type of serpentine mineral you form. And it just so happens that I guess in this interpretive framework, Ben argued in that paper that it just so happens that most of the hydrogen that you produce in these off-axis serpentinizing systems, these are seafloor hosted systems today, happen to be producing so much hydrogen because modern seawater is low in silica, and that's because the diatoms and the other siliceous organisms are using it all. But of course, early in Earth's history, that was probably not the case, right? So if you don't have anyone using marine silica, and silica concentrations are higher, by Ben's estimates, hydrogen production in the off-axis systems might have been up to 2 orders of magnitude than their counterparts, modern counterparts. So yeah, that's just kind of a quick synopsis. And I think themes that Alexis touched upon in her talk, kind of mentioning that field work, laboratory work, and kind of improving our predictive capability of understanding these reactions is the way forward here. I mean, Ben's work is just an example of kind of a broader suite of studies that are trying to do that. So it's
the beautiful thing about, oh, sorry, go ahead.
Well, I was just going to follow on just briefly on the details of that, because when that paper, this is Tutelo, I guess it's 2020. All the years are blurring with post-COVID right now.
Yeah.
It's like,
yeah.
It feels like a long time ago right now. There's when that paper, the seawater throttle paper came out, I really had to puzzle over that, and it's just beautiful work on what's happening under low temperature conditions, the way you put iron-3 into the structure of serpentine, what controls that. And we've been long thinking about how silica forced minerals like brucite to convert into serpentine and how hydrogen got made. And I thought, oh, this is so interesting. You're predicting that there'll be much lower global fluxes of hydrogen. And I rarely look at global fluxes. You and Barb do this much more, but you're often trying to, both Earth and Mars, think about hydrogen and its role in warming of the planet. But so I jumped and I thought about what we study in these terrestrial systems. And I went, well, wait a second, we do see this mechanism at play. We see the ferric serpentine. We have serpentine with almost entirely iron-3, 80–90% iron-3 in our rock systems that form there. But we are at low silica activities as well, because we are not the ocean. So when you introduce a rainwater directly into these kinds of rocks, the rocks buffer the fluids to extraordinarily low silica activities. And then we look at all these fluid mixing processes going on, higher and lower silica fluids, and boom, you can make serpentine, you can make hydrogen. And so it made me realize that that there's two different things going on. And if we go back to this early state of the planet, the ocean, as you're saying, maybe but much higher silica activity, and it really may have suppressed this mechanism of hydrogen formation in ultramafic rocks. But I don't think that would have suppressed hydrogen locally in continental states. I think what we're seeing in like the Oman subsurface is much more analogous to what would have happened. So then we get forced to this question that I do not have a good answer for, but how much continent there is and how much ultramafic rocks exposed to rainwater, etc. But I do think that that's a segregated sort of island, a local area that we could still achieve very high hydrogen activities and a lot of the processes we've talked about today, even if the ocean at that time was suppressed and was globally keeping a lower hydrogen. So that's just something that's been on my mind since reading that.
So it may be that when we look back in time, we may be looking now. I mean, one of the slides I went past quite quickly was this nice work by Oliver Warr a couple of years ago, who went through and he took a look at all of our sites and was able to show the amounts of hydrogen for serpentinization go up and down a lot, roughly as a function of bulk mineralogy and the presence or absence of mafic or ultramafic rock minerals. But the radiolytic contribution is pretty much the same. I mean, it does vary as a function of uranium, thorium, potassium, but there's less noise in that. So it might be that in the early Earth, hydrogen from radiolysis was higher, hydrogen from serpentinization maybe was lower. But again, I think that's sort of where the heads are nodding. That would be the back of the envelope that all of us have come to now, particularly in the light of Ben and Nick's beautiful work. But what it really shows us is how much fruitful areas there are to investigate, one. And two, I think the key point is, regardless of how much those rates went up or went down, we now have a much better sense of what some of that prebiotic chemistry might have looked like. Now that we're really taking on board something beyond just the surface chemistry and direct atmospheric. So we're moving away from thinking about the early Earth in the context of the atmosphere and its communication with just the near surface. And we're recognizing if we really want to understand the coevolution of Earth and life, then we need to go, as we say in our C4 group, we need to go into 4 dimensions. We need to go deep and look at the whole planet. And we need to do that over time, which is the 4th dimension.
Oh, Barb, one thing I found the paper that you published this year just astounding with these acetate concentrations you found, and then the mechanism that of invoking carbonate reactions that are being induced by radiolysis. And that just, again, as you talked about today, opens this whole new world of possible reaction networks. And although you have this sort of extreme end member case, which showed that there was clearly something anomalous going on, and you've produced so much acetate and formate, for example, the idea that in other systems, though, that have shorter residence time, you still would be getting a constant bleed or a flux of acetate and maybe oxalate and other compounds into a system. And that's very intriguing. It might be just in micromolar concentrations, but it would be persistent.
Yeah, and then, oh, sorry, go ahead. Yeah, I think you've really hit the nail on the head, because what that does is it makes the South African system really exciting. Because end members, and thank God we have end members because they help us refine the processes that are at play. But a system like the Witwatersrand Basin is also extremely exciting because there, just as Alexis has invoked, what we may see is a bleed of abiotic, but then we know there's some intense microbial communities cycling within the Witwatersrand Basin system. We have them at Kidd Creek too, but they're very low biomass. They're clearly operating at very slow rates, and whatever they're doing, I would argue, isn't enough to really impact the acetate and formate, or we wouldn't have exactly the same concentrations and isotopic compositions over 10 years. Those microbes are not getting at the acetate and formate, but not so in the Witwatersrand Basin. And so I think that provides us with a really fascinating experimental playground where we might be able to begin to tease apart then that the relative impact of the abiotic and the biotic processes. And indeed, it's why I'm so excited about your work in Oman as well, Alexis, because I think these areas where you do get mixing, where you do have interconnection between the subsurface and the surface, they provide that opportunity to take a look at the gradients in a different way. I'm really enjoyed seeing the overlay. I know you didn't get a chance to talk about it today, but I think it's fascinating the way the microbial community structures appear to change as a function of many of the geochemical gradients that you've elucidated.
Well, the irony there is we went in to study subsurface life, and there's 1,000 things we'll continue working on with that. But part of my heart keeps wishing that it wasn't so alive, because I think if we didn't have that overprint, it would be an absolutely beautiful system in which to really understand what some of the potentially prebiotic reaction networks would look like. And coming back to Paul's question, though, that where some of the inputs are the same, and some of the modern things like oxygen, it's fine, it's removed very quickly, but we can't currently in the modern load cyanide in, for example, which I would love to see its fate in such a system. So this is where we have to move to experiments and modeling. But at least we can have a more informed mineralogical framework in which to do that.
Excellent. All of this discussion of the subsurface has encouraged me to ask kind of an oddball question. I hope it doesn't completely derail the conversation, but I was really interested in the sort of idea of the life without photosynthesis, and you can even have life outside of what the sort of traditional liquid water habitable zone is. With this subsurface life, you could even imagine a subsurface water-based life, you know, under the ground of Titan or something like this. The struggle that an astronomer is going to have with that, though, is what do you look for? It's going to be very difficult to go to an exoplanet, for example, and dig beneath the surface. I mean, it would even be beyond our current capabilities to do that with Titan. You did say that the residence times are long, but they're not infinitely long. Is there any sort of imprint that might be possible in the atmosphere where we might have a hope to see it?
Absolutely. And when I'm not doing this with you, I'm amongst 120 other people who are living and breathing the decadal survey for planetary sciences and astrobiology. And our first set of chapters is due next week. So we've been discussing this oh my goodness, yeah, over and over. There's all kinds of really creative ideas about that. I think the key thing relates back to what I said a moment ago. You know, atmosphere, surface, subsurface, we need to recognize that these are systems that are interlinked. And indeed, when we say we should be interested in the subsurface elsewhere in the solar system and even out to the exoplanets, it doesn't mean the only way to get at that is to drill. The subsurface is already interacting and speaking to the surface. I remember the first time Bethany Ellman was talking to me the way Nick just did about Gale Crater. I remember, who needs a borehole if you've got Gale Crater? That thing is incising the crust of Mars incredibly deep. And indeed, the richness of the information they've gotten from that speaks to that. So places where you have impact, places where you have scarps and topography, fractured terrains, lava tubes, all of these vents, such as you see here in these pictures, which are still up from Enceladus and Europa, any places where you've got that, there's places where the subsurface is coming right up to you. And so, for instance, how would you sample the subsurface in Europa and Enceladus? Well, they're already doing it. because they're looking at these plumes, and these plumes are a function of subsurface processes. The information that Curiosity has given us on the methane on Mars, I think in the end, will clearly speak to subsurface processes as well. At least that's my own bias. And then the question then out to exoplanets is the same, because of course, what forms an atmosphere? Even at the level of volcanism, we know subsurface processes contribute to the characteristics of the atmosphere.
Oh, sure.
And so indeed, this may change the nature of what kinds of signals we tell the astronomers to look for in exoplanets. But we've already seen that. We're already evolving beyond the idea that you just want to go out and find oxygen. I'm sure we'll all be excited if we see oxygen in an exoplanet, but we all also recognize that for this planet, for the first 2.5 billion years of its history, not finding oxygen would have been a false negative. We had lots of life long before we had oxygen in our atmosphere. So I think it contributes to just this broader, more comprehensive, more universal question of what a biosignature is these days.
No, I think that that's a really good point, and I think that feeds into the ambitious project of Sarah Seeger looking at the all small molecules. And then the next question, which you may not have a good answer to yet, would be which of those small molecules would be a good one to look for that's a biosignature for subsurface life, or which isotope, because there was just a recent paper about detecting the first isotope on an exoplanet. So do you have anything to say about that, or is that all for future work?
Oh, I've always got lots to say, but I want to yield the floor for a minute to these two.
Okay.
And
All
then
right.
if there's still
Sure.
time, I'll say what I say, which is.
Okay, yeah. If you do have the name for a particular molecule, I'd be very, very interested in what that molecule would be. But
For me, it's ratios.
Okay, cool.
Ratios. That's
Okay.
to me what's more than the presence or absence of any particular molecule. It's the ratios of certain molecules that intrigue me.
Cool.
Alexis
then-
or Nick,
Yeah.
did you want to have a shot at that one?
Sorry, you broke up, Paul, when you were asking that. Could you repeat the question, please?
Oh, sure. And I might expand it a little bit to touch on one of your sort of hydrogen generation processes. I was asking about whether there would be any atmospheric biosignatures for subsurface life, how the subsurface would react with the surface and eventually the atmosphere, because of course for exoplanet people especially, but even for astronomers in general, atmospheric biosignatures are usually a little bit more accessible. And then expanding that a little bit also, I'd be interested in your idea about whether you'd be able to see these sorts of periodic tufts of hydrogen, whether there'd be any sort of potential about seeing those on particular exoplanets of a certain age.
Okay, thanks, Paul. Yeah, I guess when you had cut out, I thought you asked a different question, but I didn't realize that you were asking us to sort of weigh in on the question we've been discussing over the last 5 to 10 minutes. I mean, as far as the hydrogen production is concerned, I mean, I'm not really sure I'd go as far as to say I can think of any obvious characteristics that would render it a biosignature. I mean, I do know that this has prompted a lot more research into, how reducing atmospheres form and evolve, period, because they have fascinating climatic and prebiotic chemical implications. As I think as Barb mentioned, ratios or maybe even beyond ratios, but combination of elements that exist in obvious chemical disequilibrium. I think I kind of like the general utility of that characteristic as a biosignature. I think this is something that David Catling has published on, which seems to jive well with me. So that would sort of be my my response to it.
Great.
I would just add a little bit in that I think there's a lot of interesting work going on right now to determining, depending upon what you call essentially your seed set of molecules you think would be present. So since we've been talking about abiotic processes today, what are your subset of chemicals you really believe could be present on a planetary body? And again, I wouldn't do it in the atmosphere, but like what's reacting in the subsurface. And I think our ability to better predict the reaction networks that can happen, which is very much dependent on what mechanisms we understand or not. And that's true in the biology, what biochemical pathways we know, and it's very true if we want to do this in a more abiotic fashion. We have to really understand what mechanisms can occur. And so Barb's just added one in today that would then change your reaction network you would propose in the subsurface. As those mature significantly, that will give us a different window of what we think the distribution of products might be, that would be in part communicated back to the atmosphere and detected. So I think we don't have the smoking gun molecule, but we might start getting to better understanding, if we could understand a distribution of molecules in that system, what the networks were, biological or abiological, that produced them. So that area seems to be advancing in profitable ways, but will continue to require a lot of communication between disciplines.
And I think that that's a really, really nice note to end on. I especially like it because it mentions networks and fleshing out those particular chemical networks to make sure that we aren't missing something, something critical. Well, I would very much like to thank you all for coming and generating a lot of really, really interesting conversation for our small gathering here. So thank you so much for your time, and thank you so much for the wealth of very, very interesting ideas.
It was really fun and just a great pleasure. Thank you, Paul and Nick and Alexis and everybody.
All right. Thank you all.
Thank you.
Thank you.
Goodbye.
Bye.